let's see how we can use the charts and some of the other issues that we are looking at, which is a slightly simpler version than doing all the method of slices. Once again, I would like to say this approach is called limit equilibrium approach. I have the slope here of height h, and you are assuming a trial arc with a radius r2, and weight here is W1, weight of the soil, center of gravity is here. You may sometimes consider if there is any additional load on the top, this is called external load, and you can also take that into consideration. And if you know where this is, suppose you have put in a tower on top, then the weight of the tower comes into picture, and you take the moment of that, W into x2. And in case of a purely cohesive soil, suppose I have only cohesive soil, then the only strength we get is the underlying strength Cu. So the strength mobilized is equal to Cu into this arc length L, which is equal to the radius r times this angle theta. And what is the moment? Equal to m, because all these forces are at a distance, radial distance r. So you get the moment, resisting moment is equal to tau, that is equal to Cu into length of the arc, which is equal to r into this angle theta and into r. So you can get the factor of safety by this simple approach. And if, for example, in the summer it has been very dry and you find that there is a crack formed, and at the end of summer the most critical period would be the rain came and then this is full of water. So this is called a tension crack. With that you will have water pressure here, and then we add it up here and saying that this water pressure also causes failure. In the phi naught analysis, phi u analysis, you have to consider the additional force due to water pressure. The maximum depth of crack is generally twice Cu by gamma, is what we have determined from the capillarity, and we find out the factor of safety. Please remember that if there is a tension crack possibility, that is more critical. So usually in the dry season, that is say starting from March to May, June, you have very hot summers and you get this crack, and the first time the rain occurs, water will go inside and try to push this. This is a very critical one too, you have to consider. So in order to do this, we have different types of charts which have been given. Let's look at only Taylor. These are all advanced ones, we don't look at it. Here is the Tailless chart. He has considered a slope of height h. The soil has only underlying strength Cu. The hard stratum is at a depth d times h. So if I look at the parameter d, if d is infinity, the hard stratum is far below, whereas if it is 1, 2, etc., it is closer to it. So he has done the whole analysis and he gives the results in terms of stability number, which is equal to Cu by f into gamma h. So what we do is I have beta, the slope angle, and if I know the thickness of the clay layer, I can go. Suppose I look at infinity, a very high value, the stability number varies from something like 1.8, and for steeper slopes it becomes higher, goes up to around 2.6, 2.7. So I can easily calculate factor of safety is equal to Cu, you have found out NF, you know gamma, unit weight of the soil, you know the height of the slope. I can get factor of safety straight away from this chart. I don't have to do a method of slices analysis, etc. If you have a finite layer, for example, this hard stratum is at a depth, d is 1, which means it's here, d is 2 means twice the height, etc. And then you can see the stability number becomes smaller, which means the failure surface, if I look at this, it cannot go into the soft clay, so the factor of safety will be higher. If stability number is smaller, the factor of safety will be higher, because factor of safety is equal to Cu by stability number into gamma into H. So if the hard stratum is at shallower depths, we get a higher factor of safety. If the hard stratum is down below, you will have smaller factor of safety. Straight away, using the chart, you can get it. Only problem is you may not always have some homogeneous conditions. And you can also, if you want to, find out the critical locations. So this gives me where the slip circle, where the points are in terms of the, this is the coastal soil undrained condition, same chart. But next one, we have a lot of software now which gives me the factor of safety by just giving input. This is the most popular one, Geoslope, which is available in the market. We should use that to get it. And it automatically determines the minimum factor of safety, eliminates the need for iterative solutions, and enables, you can do different cases without any problem. So if I look at it, I just give these coordinates to the computer, give the geometry, and you may have different type of soil layers. I provide the zone in which I am searching for the minimum value. All that can be given by a menu driven by this. And the last one I would like to mention is earthquake conditions. So when we have an earthquake, we have to consider additional forces due to seismic force. These are for earth dams. We look at various conditions. This is the steady seepage. This is the sudden drawdown condition. On the downstream side, you can see the flow net. If I take the arc here, I have to consider the pore pressure based on the equipotential line through the slice. If I have sudden drawdown, the water level has come down from this full reservoir level to here, but the pore pressures remain as they are from steady seepage. So I now look at these pore pressures and calculate at the dam slope stability. This is what called sudden or rapid drawdown condition, and we find out the factor of safety.